Okay, we've been talking chapter 9 and stoichiometry, and last time we got into limiting reagents and the idea of limiting reagents. And the idea of limiting reagents, as we talked about, is in any type of reaction, there will always be a reagent or reactant that gets used up first, and that is the limiting reagent. So again, if we have this reaction here, where we need A and B coming together to form our product, if A was our limiting reactant, which is the one that gets used up first, and B would be what is known as the excess reagent. And that is the one that you have plenty of, you have some left over and the reaction's done. The sort of significance of limiting reagents and sort of excess reagents is it is always the limiting reagent that determines how much product that you make. Because again, we just a very simple example here, as I mentioned last time, as soon as, for example, A gets used up, there is no possible way for you to make any more product at that point because obviously you need A to make the product. And because it gets used up first, it is the one that limits how much product you can produce. And how do you know it is a sort of limiting reagent problem versus a basic stoichiometry problem like we talked about? The way that you can recognize it is a limiting reagent problem, you need to kind of do that calculation is based on what's given to you. So if you're given enough information to calculate the moles of each reactant, that is the biggest clue that this is a limiting reagent type of problem, and you have to do that. So if you think about, again, like some of the basic stoichiometry problems that we did earlier, we were really only given one piece of information, maybe one reactant, maybe how much product. But definitely in a limiting reagent problem, you're given enough information about both reactants. There could be more than two, but in most cases, there'll be two. In most reactants, for both reactants to get to moles. And those could be any units that they may give you. But if you have the units given to you that you could do several conversions or a couple of conversions to get the moles of each one, it definitely is a limiting reagent problem. So we talked about kind of two approaches to it. One sort of follows the same sort of basic stoichiometry steps that we did before, which is, again, balance the equation, convert what they give you to moles. And right around here at this step, you do need to do a limiting reagent calculation. And remember that in order to determine the limiting reagent, it is based off of a calculation. Very commonly, people will sometimes get to the second step here and they'll convert each of the starting reactants into moles and go, oh, that guy is the smaller number of moles, so that's the limiting reagent. And that is not how you can pick it out. It's not always the case. You do have to determine limiting reagent through a calculation. You can't just compare the moles that you're starting with of each and go, that one's smaller, so that's going to be a limiting reagent. So it will not always work out that way. It has to be sort of calculation based. So in this method, the process here is basically you pick one of the reactants and do a stoichiometry problem to figure out how much of the other, thank you, reactant is needed. So in this case, this is kind of like your starting amount here in the second step. You're going to do just a small little calculation between the two reactants. And if you want to use up one of the reactants completely, you're going to figure out how much of the other one is needed. And what you're going to do with that is then compare to your starting amounts. And if you have enough of whatever reactant you are looking to use or need, then that means that that's the excess reagent. If you compared to how much you need to how much you started with and you do not have enough, you have less than that, then that's going to be your limiting reagent. The good news is if you can determine which reactant is the limiting reagent, by default, the other one's the excess, and vice versa. If you can figure out which one's the excess reagent, by default, the other one will be the limiting. So you really only have to figure out one of those things, and it will tell you which one's the limiting reagent. Once you do that, that's pretty much it. You're just going to roll through the rest of the sort of calculation like normal. You then will use your limiting reagent to do the mole relationship. And you do want to use, obviously, the starting amount of your limiting reagent. And then lastly here, you're going to take those moles and convert them to some other unit, like a normal sort of process. So this is the process for doing a limiting reagent problem. Again, like we talked about, pretty much kind of fits in with our basic stoichiometry sort of steps. The other way that we talked about that you could do this, which is a commonly way that's sometimes taught these days, is you just basically do two separate calculations. And you basically just kind of take the first reactant and basically do a stoichiometry calculation, those 4 steps, all the way through to the product. And then you do a separate calculation from the other reactant to the product. And whichever one gives you the smaller amount of product is both your theoretical yield and your limiting reagent. So the smaller product is your limiting reagent. So that is the other approach. You basically will just throw out one of the calculations. You won't use it for anything. And basically the other one will tell you. So that's the other sort of very common sort of way that it is taught. Any questions on that there? All right, so we kind of went through a little example there towards the end, but let's take a look at this one together and kind of go through it. So first off, if we take this reaction here and we are going to react 6.83 grams of iron with 9.34 grams of sulfur, we really want to know how much product we're going to produce. So we want to know basically how much product here. Grams. So the first thing that I want to always sort of look at when I'm doing a stoichiometry problem is this a limiting reagent type problem or not? So that's an important thing to sort of figure out up front. And the one thing that I see in this particular case is I do have grams of iron given to me. I do have grams of the sulfur given to me. And I do know, hopefully, that from grams, you could definitely get to moles, right? So that right there tells me, because I am given enough information about both of the reactants here, I could definitely get to moles of both reactants. It is a limiting reagent type problem. So once again, we have to at some point do that limiting reagent calculation to determine which one it is. So really, I'm going to follow the steps there, the 4 steps within the middle. We're going to determine our limiting reagent. So step number 1 in any sort of method that you choose is always with stoichiometry. Make sure that you have the equation and it's balanced, and in this case it is. We got 1 iron on each side and 1 sulfur on each side. Second is to convert to moles, which we do need to do. So we're going to convert to moles. So here we're going to take our 6.83 grams of iron. We're going to use the molar mass from the periodic table for iron, which is 5585 there. And we're going to put those on the bottom, 5585 grams per mole of iron. That's going to give us really our starting amount of iron in moles. So 6.83, my calculator wakes up, 6.83 divided by 5585. That's going to give us 0.122, and I'm not going to round too much here. We'll go to 3 moles of iron. We're going to do the exact same thing with our other reactant because we could do that, and that is 9.34 grams of sulfur. We would go to the periodic table and look underneath sulfur, and it will say 3207. And we're going to put the grams on the bottom there, moles of sulfur up on top so that the grams cancel. 9.34 divided by 3207, going to get us 0.291, we'll call it 2 moles of sulfur. So once again, you can think of these as your starting amount of each of the reactants in this case. All we simply did is convert it to some other unit. And now we're ready at this point to do our limiting reagent calculation. So basically the first two steps, no matter what method you choose, are pretty much the same. Here we're going to do our calculation. And remember that when you do your calculation, you really could choose either reactant. And what you're trying to figure out is if I want to use up all of that reactant, how much of the other one I need to put in there with it. So in this case, I'm going to try to figure out how much sulfur is needed to use up all of the iron. And this is going to be really my limiting reagent calculation in this point. So to do that, I'm going to take my iron, which is 0.1223 moles of it, and I'm going to do just a basic stoichiometry relationship between iron and sulfur. And from the balanced equation, we can see it is 1 mole of iron, which will go on the bottom, will give us 1 mole of sulfur. And again, that is the mole to mole relationship from the balanced equation, which is the coefficients. The moles of iron are going to cancel, and that will tell us I need 0.1223 moles of sulfur is needed. First off, any questions on that calculation? So again, this calculation is solely for us to determine which one is the limiting reagent. Any questions on that? All right, what we're going to now do is compare how much we need of sulfur to how much sulfur we're starting with. So we're going to compare these guys. And in this particular case, I need 0.122 moles of sulfur. I am starting with 0.2912 moles of it. Do I have enough sulfur in this case? I do. I got plenty of it. And because I have enough, what that means is the sulfur is going to be my excess reagent because I have enough. And by default, because I'm able to figure that out, it will tell me that the iron will be my limiting reagent. I actually don't need to do the next calculation. I just know by default the iron in this case will be the limiting reagent. Any questions on that? So that was the calculation base to figure out our limiting reagent. At this point, we are ready now to actually just finish the problem. We can now pick up back with our third step, which is we're going to use the limiting reagent, starting amount, and figure out how much product we're going to make. So third step here, we're going to take our limiting reagent, and we're going to take the starting amount of our limiting reagent, 0.1223 moles of iron. And now we're going to do the relationship between our limiting reagent and our product, which is kind of what we're interested in. And that also, in this particular case, happens to be a 1 mole to 1 mole relationship based off of the coefficient. And that is what we're going to use here. And I could take 1 mole of iron based on the equation will now give me 1 mole of my product. And once again, I am starting with the starting amount of my limiting reagent. So that's really important here. That is going to cancel out the moles, and I'm going to end up with 0.1223 moles of iron 2 sulfide. Now I want grams, so I'm going to need to do step number 4, which is convert those moles into some other unit. And in this case, I will have to add up my molar mass of FeS, and that's going to be 5585 for the iron plus 3207 for the sulfur. That's going to give me here 5585 plus 3207, about 8792 as the molar mass. Remember, that's going to be my conversion factor. It's going to allow me to figure out the grams. So using the grams up on top, moles on the bottom, moles are now going to cancel, and we will end up with about 10.8 grams of FeS. This would be, once again, the theoretical yield in grams. By the way, this would be the theoretical yield in moles, right? So you can do moles or grams in this particular case. So this method, again, is basically the same four steps that we use in a basic stoichiometry problem. As you can see in the middle, you just got to do that little calculation to determine the limiting reagent. Any, first off, questions on that there? Now, as I mentioned the other day, there is also a very common question that's sometimes asked, which is how much of the excess reagent will be left over at the end of the reaction. So you could actually do that calculation as well. So let us, maybe I can do it this way, get rid of some of that. There you go. I'll do it up on top, I think. Now, if we were interested in this case of how much of our excess reagent is left over, we can do that by taking our limiting reagent calculation, and we happen to have chose correctly here because this is our excess reagent. And based on that calculation, we saw that we needed for our excess reagent, we needed 0.1223 moles of it. We know that we are starting with 0.2912. So we are starting with 0.2912 moles. That's what we're starting with of our excess reagent. We know based on our calculation for the limiting reagent, we need 0.1223 moles of it needed. And that will tell us that at the end of this reaction, we will have left over about 0.1689 moles of, it was sulfur. And if we use the molar mass of sulfur, 3207 grams per mole, we will know that we will have left over, if I pop the right number in there, about 5.42 grams of sulfur is left over in this particular case. So by doing that limiting reagent calculation, we got lucky and we actually had the information needed to figure out how much of our excess reagents left over. Now, if you happen to have done the opposite calculation there in the middle and figured out how much iron you needed, you would not have had that calculation. You would then have to go back and kind of do that calculation to figure out how much of the excess is left over. Any questions? And obviously for our sulfur, we started with 9.34 grams of it. We have 5 grams left over, so we use just under 4 grams in the actual reaction in this particular case, as that is how much we actually started with. That's how much is left over of it. Obviously, for our limiting reagent, we have nothing left over, right? Because it gets used up. So ideally, we have pretty much 0 of that left over. Any questions on that calculation there? All right, so let's see here. I tried one. See here. All right, so why don't you try this one here and see what you come up with. We want to calculate the mass of our product that is formed here. There's some molar masses given to you, so you don't have to calculate them. So that's pretty good. All right, so give it a go and see what you come up with. Good look, see how you're doing. A couple things on this one. Again, we're looking for grams of our product here. They definitely will not always tell you it's a limiting reagent problem, and most of the time they will not tell you it is a limiting reagent problem. So again, the way that we can recognize this as a limiting reagent problem is we are given the grams of this guy here, one reactant, and also the grams of another reactant. So definitely because we have the grams of both reactants, we could definitely get to moles of both of them. And again, that is the thing that you want to look for. I would say probably almost 100% of the time, they will never ask you or tell you in a problem that this is like a limiting reagent problem or something like that. So you want to be able to kind of recognize that you need to do that step. So now that we do know that it is a limiting reagent problem, because we can get the moles of both reactants, what we want to do is just follow our steps. Step number one, it's already balanced, which is good. Step number two, we want to take whatever they gave us and convert to moles. So we're going to do that. So we're going to take our 622.7 grams of NH3. They were nice in this problem as well and gave you the molar mass, which normally they do not. So normally you do need to go to the periodic table and calculate your own molar mass. And in this case, it's 1703 grams per mole of NH3. And that's going to get us 622.7 divided by 1703, which is from the periodic table, 36 point, I'll call it 56. That's good, I think, moles of NH3. We're also going to do the same thing with our other reactant, which is 1,241 grams of CO2. They also gave the molar mass of CO2, which you would need to go to the periodic table in most cases and calculate yourself. And that's 4401. So 1241 divided by 4401 gives us 28 point, we'll call it 20 moles of CO2 in this case. So once again, you could think of both of these guys as your starting amount of each reactant. So because again, it is a limiting reagent problem, we do need to do our calculation. And as we talked about previously, again, you could choose either reactant. So in this case, if I want to know how much CO2 is needed to use up all of the NH3, that is going to be my calculation to determine kind of which one is the limiting reagent calculation here. So to do that, I'm going to start with my NH3 moles, which is 36.56 moles of NH3. I am going to go to the equation and just do a mole-to-mole relationship between the two reactants. And from the equation, we see, based on the coefficient, that for every 2 moles of NH3 you put in there, you also need to put in there 1 mole of CO2. The moles of NH3 will cancel, and that will get us here basically 3656 divided by 2, about 1828 moles of CO2 is needed. First off, any questions on that calculation? At this point, we can now compare how many moles of CO2 we need to how many moles of CO2 we started with when we compare. And on that comparing there, we do see that we need about 18 moles. We have 28 moles of it to start with. We do have enough. So again, because we have enough of it, that means the CO2 here is our excess reagent. And by default, the NH3 is going to be our limiting reagent. Any questions on how to determine that there? Now that we've determined which one is our limiting reagent, we really could just pick back up into our basic stoichiometry sort of situation. And we could start with our limiting reagent. And it's important to make sure that you do start with the starting amount of your limiting reagent. So that's going to be, in this case, my 36.56 moles of NH3, as that's my limiting reagent. I can now do between my limiting reagent and my product, the mole-to-mole relationship from the equation. And from the equation, we see for every 2 moles of NH3, we get 1 mole of NH2CO. These guys are going to cancel, and that's going to get us here basically the same number as above, about 1828 moles of our product here. This, by the way, would be our theoretical yield in moles of our product, but we are interested in how many grams of our product, so we do want to convert our moles to grams. And in this case, they were also nice enough to give you the molar mass from the periodic table. If they didn't, again, you would need to go to the periodic table and calculate it. And we'll just use that right here for our fourth step. which is we're going to take the grams up on top, the moles of our product on the bottom. And again, those guys are going to cancel. And that is going to get us here times 6006. About 1,098 grams of our product here is going to be produced. And in this case, that looks okay since our numbers were about 4 significant figures for each of our numbers. So we should be good. This would be, again, our theoretical yield in grams in this case. First off, any questions on those calculations there? Now, just like in the previous problem, if we wanted to figure out how much of our excess reagent is left over, we could actually do that as well by using our limiting reagent calculation, because we did kind of choose correctly here, so that was not too bad. So again, using our limiting reagent, how much of our excess left over? So the CO2 was our excess, and we started with 28.2 moles of it. We figured out from our calculation that we needed 18.28 moles of it. It's needed. That will give us a net of 20 minus 1828 of about 9.92 moles of CO2 left over, which again, if we use the molar mass of CO2, 4401. That will tell us that in grams, we got about 436.6 grams of CO2 left over, right? We started with about 1,241 grams of it. So, we use about 800 grams or so in this reaction. We got about 400 grams of it left over. Any questions? And in this case, again, we kind of chose right on our limiting reagent calculation. If we chose the other calculation, you would have to go back and do this calculation to figure that out. Any questions on any of that there? All right. So we'll go through here, kind of show this. This is what we just talked about. There we go, a little bit more. We got the same answer, so that's good. All right. All right. Let's talk then about yields of our reactions, and we talked a little bit about it in lab on Monday. There really are 3 types of yields. And again, when we talk about yields, we are talking about products. So we never talk about yields in terms of reactants. A yield is basically what is formed as a result of the reaction. So that is always talking about a product when you're calculating some type of yield. We talked about, obviously, both of these here, but just to reiterate, the theoretical yield is your maximum amount of product that you should be able to be produced in that reaction if everything went perfect. There was no side reactions. You didn't lose anything. For example, like on your beaker walls, when you're doing your experiment, or on your glass stirring rod, there's some of that yellow that was just sitting there, right? That's yield that technically was lost in the result of your reaction. But if everything went perfect, that is the maximum amount of product you should be able to be produced in that reaction. What actually happens in a reaction, as you saw on Monday, is you get what is known as the actual yield. And that is what is actually produced as a result of you doing the experiment or the reaction. The actual yield is usually smaller than the theoretical yield because, again, things are not perfect. In book problems, the actual yield is always given to you, usually in the problem. So usually somewhere in the problem, they'll tell you, hey, you produce this amount of the product. They'll always give you that number in a book type problem. So this is usually given to you in the actual problem. Now, the theoretical yield, you may have to calculate. And in a lot of cases, you do have to calculate it. And calculating the theoretical yield could be one of 2 situations. It could just be a basic stoichiometry problem like we did at the beginning of the chapter, or it could be a limiting reagent type problem that you have to do. But you have to do some type of stoichiometry type calculation to figure out the theoretical yield. The third type of yield is what we were really looking for in that experiment, which is the percent yield, where you take the actual yield, which is typically given to you in a book type problem, divided by the theoretical yield, which is typically what you calculate, and times it by 100. You calculated your theoretical yield on Monday based off of how many grams of the Ki you weighed out. That was the limiting reagent. And based on those grams, you can figure out how much product you should produce, and that's your theoretical yield. Your actual yield obviously is whatever was on the filter paper, right? The yellow solid that you had left over at the end of the experiment. Now, like I said, usually for percent yield, we're looking for a high number. Close to 100 is good, and then high 90s, mid 90s is really good. You typically do not want to go over 100% yield. And typically, if you go over 100% yield, that usually is a result of an error that was made somewhere. So, how could you get over 100% yield? The most common way is, for example, like what we did in the experiment, you filtered out your solid on the filter paper and maybe you didn't let it dry completely and you still have water weight on your filter paper. So when you go weigh it, you're going to get all that water weight with your solid and you're going to count it as your solid's weight. And now your solid is bloated with water weight that's really not your solid. And now you have over 100% yield. So that's a very, very common way that people sometimes will end up with over 100% yield. It's again, if that solid is not completely um, dried out, say on the filter paper, or if there's some type of impurity or something that comes along in the reaction, maybe some type of side reaction creates some type of impurity. And that's also, again, another way that sometimes you can get over 100% yield. So in most cases, not a good thing to go over 100%, especially if you're well over 100%. That's usually not a really good thing. Any questions on that? To calculate the percent yield, most of the time we use grams over grams, so actual yield in grams and theoretical yield in grams as well. But to be truthfully honest with you, it doesn't really matter the units. You can do it in moles over moles. As long as the top number and the bottom number here are the same units, you can calculate the theoretical yield, or sorry, the percent yield. So you can do moles over moles, but most of the time you're going to do grams over grams, but definitely can do it moles over moles as well. All right, so why don't you, let's maybe, yeah, let's get this one actually. Let's take a look at, let's do this one here. All right, same reaction we just used. So you have the molar masses and everything with you from the previous problem. If we take the 100 grams of ammonia and react it with 100 grams of carbon dioxide, and 120 grams of your product is produced, what is the percent yield? So take a few moments there and see what you come up with. And again, these are the same ones we just used in that previous problem. So you got all the molar masses there that you can still use. Okay, let's take a look. So in this case, we have 100 grams of ammonia. We're reacting with the 100 grams of carbon dioxide. We produce 120 grams of our product. We want our percent yield. We have some molar masses from our previous example, which are the same thing. So obviously, if we did do that previous example, you would need to look up those molar masses probably on the periodic table. So the first thing we want to think about is we are looking for our percent yield, which is again our actual divided by our theoretical times 100%. So, like I mentioned before, typically in book type problems, they do give you the actual here. So, we do have our actual just sort of given to us. Also, very common, the theoretical is usually not given to you, so you usually have to calculate that. So because we do need to calculate our theoretical yield, which really comes from a stoichiometry calculation, what we need to determine again is it a basic stoichiometry problem or is it a limiting reagent problem? So in this particular case, we are given the grams of each reactant That again tells us we could definitely get to moles of each of those. And because we could get to moles of each of the reactants, that is the key that this is a limiting reagent problem. And we do need to do that step along the way. So our sort of first two steps, as we've been talking about, is our normal steps where we got our equation and its balance. We're then going to take each of our reactants that were given to us and we're going to convert them to moles, which is our next sort of step along the way. So we have 100 grams of NH3, and again, using that molar mass from the previous problem, 1703 grams per mole of NH3 will get us into our moles. So we'll take 100 divided by 1703, going to get us a 5.8, come here, 5.872 moles of NH3. We'll do the same thing for our other reactant, 100 grams of CO2, using the molar mass from the previous problem, 4401 grams per mole. Obviously, also could get from the periodic table by adding everybody together. 100 divided by 4401, going to get us 2.272 moles of CO2. Once again, you could just sort of think of these as your starting amounts of each of these. We have now come to the point of the calculation where we want to determine which one is the limiting reagent problem. And as we've been talking about, again, it doesn't really matter which one you choose. So here, to figure out my limiting reagent sort of calculation, I'm going to figure out how much CO2 is needed. So how much CO2 is needed to use up all the NH3. So starting with my NH3, which is 5.872 moles of NH3. Remember, just going to do a simple little stoichiometry problem between our two reactants. So from the equation, we can see it's a 2-to-1 relationship. So for every 2 moles of NH3 from the coefficient, in the equation, we get 1 mole of CO2. So that's going to tell us here, 5.872 divided by 2, that we need 2.936 moles of CO2 is needed in this case. Remember, once we figure out how much is needed, we're going to compare to our starting amount of it. And in this particular case, do we have enough CO2? We do not, right? We need, in this case, 2.9. We are starting with 2.2, so we do not have enough. And because it is not enough, that tells us that in this particular case, the CO2 is our limiting reagent, and our excess reagent is our NH3. Any questions on that there? Once we've determined that, obviously, in this case, the CO2 is our excess reagent, we will use that to figure out how much product we produce. So taking our 2.272 moles of CO2, which is our limiting reagent. We could now go from our limiting reagent to our product, which is a 1-to-1 relationship in the equation. So 1 mole of CO2 will give us 1 mole of our product in this case. And that's going to give us 2.272 moles of our product. This, by the way, would be our theoretical yield of our product in moles. That is not very helpful to us in this particular example because our actual yields in grams. So we do need to get them to the same unit so we can calculate our percent yield. And we could use our molar mass, which is our fourth step here. And again, I'm going to use it from the previous problem, which was 60.06 here, grams per mole of our product. And that's going to get us here 2.272 times 60.06 Going to get us about 136.5 grams of our product in this case. That is our theoretical yield in grams. And that's obviously our fourth step along the way there that we normally do. Any questions up to that point? Now that we have calculated our theoretical yield, we can calculate our percent yield in this case. And to do that, I'll just erase some of this lines here. Maybe erase that as well. That's going to give us a percent yield of our actual, which is 120 grams, divided by our theoretical, which is 136.5 grams, times 100%. And that's going to get us 120 divided by 136.5, about 87.91% yield. Not terrible, not the greatest, but not horrible, I suppose. Any questions on those steps there? All right, let's take a look at one last one here to wrap up this chapter. So let's do it here. Let's say if you started with 25 grams of H2 and produced about 105 grams of NH3 in the following reaction, what is the percent yield? And we'll do a little H2 plus N2, a little NH3 here. All right, so give it a go, see what you come up with. Hydrogen, obviously 1.008. Nitrogen, 1401. And our friend hydrogen, still 1.008. I did that guy. What am I missing? That's the only two I need, actually. Don't need hydrogen twice. Got Okay, let's take a look at it since we're getting to the end here. Again, we're looking for the percent yield. So that is, it's like we just saw, our actual divided by our theoretical times 100%. In this particular case, like most problems like this, we do have our actual yield as it tells us how much of our product we produced. So that is our actual yield. We do need to calculate our theoretical yield in this particular case. And when we look at this, really the only piece of information we're given is the starting amount of H2 in this case. So because we do not have enough information to get to moles of each reactant, this is just a basic stoichiometry problem. So this is not a limiting reagent problem. It's assumed that the number they gave you, which is the H2, is the limiting reagent, and the N2 is the excess reagent. So in this case, we don't do a limiting reagents type thing because we cannot, because we're not given enough information. So again, it's important to recognize when it's a basic stoichiometry problem versus a limiting reagent type problem. So really, we're just going to follow our four steps. In this case, though, our first step here, a balanced equation, is not done. So we do need to balance it, which is always something you want to look at. And remember, we balance with our coefficients. So we need 2 nitrogens over there. We also need 3 hydrogens on the left. And now we should have a balanced equation in this case. Remember, if you do not have a balanced equation in any type of stoichiometry problem, you basically just did it wrong, right? So you got to make sure it's balanced so you have the right mole-to-mole relationship. Step number 2, we do need to do as well. We need to take the only piece of information given to us and convert it into moles. So we will need to go to the periodic table and get the molar mass of H2, which is 2 times 1.008 grams per mole, 2.016 grams per mole. So we'll do a little bit of that, 2.016 grams per mole of H2. That's going to get us here 25 divided by 2.016 Gets us about 12.40 moles of H2. Remember that this is not a limiting reagent problem, so we just continue on now to the third step, which is the mole-to-mole relationship between what we started with and our product in this case. And we can see that it is a 3-to-2 relationship, so 12.40 moles of H2. Doing the stoichiometry from the coefficients, 3 moles of H2, opposites cancel, so we want to put that on the bottom. 2 moles of NH3 up on top. That's going to get us here times 2 divided by 3 and get us about an 8.267 moles of NH3. Once again, like the previous problem, our actual yields in grams. So we do want our theoretical yield, which is what we're calculating, to also be in grams so we could calculate our percent yield. So the last step here is we will need the molar mass of NH3, and we have that from the previous problem, but just in case, 1401 for our nitrogen from the periodic table, 3 times 1.008 for our 3 hydrogens. That's going to give us our 1703 grams per mole. So figuring out here our number there, 8.267 moles of NH3, using the molar mass from the periodic table, grams up on top, so we end up with grams, moles on the bottom. Going to yield us here 8.267, basically, times 1703. About 140.8 grams of NH3. In this case, we could probably go to 141 since everybody else was 3 significant figures. And that would be our theoretical yield in grams. That would be our theoretical yield in moles in this case. First off, any questions on that part of the calculation? All right, so to finish up the problem here, we're looking for our percent yield. So once again here, I'll just steal this and put it right here. We're going to take our actual yield, which was given to us, which was 105 grams. We're going to take our theoretical yield we just calculated, which was 141 grams, times it by 100%. At least that worked out when I made up the numbers, so that's pretty good. 105 divided by 141 times 100. And not the greatest yield, 74.5% in this case, yeah. Probably lost some stuff along the way, I'm assuming, in this case. So again, this just illustrates your theoretical yield could just be a basic stoichiometry problem, could be a limiting reagent problem. So again, you want to be able to identify what you need to do in those type of problems, either limiting reagent or basic stoichiometry problems. Question on stoichiometry, percent yield, or any of that stuff? All right, that wraps up chapter 9.